Welcome to our exploration of the Sun. In this video, we'll dive into the fascinating world of our closest star. From the mysteries of coronal heating to the challenges of reaching the Sun, we'll uncover the science behind these burning questions. Get ready to be amazed by stunning visuals and cutting-edge research brought to you by NASA. Whether you're a space enthusiast or just curious about the universe, there's something here for everyone. Don't forget to like, subscribe, and hit the notification bell so you won't miss any of our exciting content. Let's embark on this solar journey together.
The Sun is a beautifully magnetically driven star, but we can't actually see magnetic field lines. They're essentially invisible, and so we have to turn to models in order for us to see the global magnetic structure of the Sun. What we're looking at here is one such model, and the color coding represents what we call open magnetic field lines, which means that they extend from within the Sun all the way out to really, really far out in space. The green and the purple have a north and a south polarity. The white lines are closed magnetic field lines, so they come out from the surface of the Sun and then they loop around and close near the solar surface. Now you can see how beautifully dynamic the Sun is as well. Magnetic field lines interact with each other. They cause big explosions to occur on the Sun, and that's one reason it's extremely important to study the magnetic structure of the Sun, especially on a global scale. And again, models are the one way we can do this because they allow us to model where the field lines are, how they're going to interact with each other when the Sun rotates, and then how that causes solar storms like coronal mass ejections and solar flares. Sometimes the Sun is quiet, sometimes the magnetic field lines aren't doing a whole lot, but other times you see these bright regions on the Sun where you have closed loops, and that's where activity can occur, where the flares can occur. So everything is really magnetically connected.
NASA's Parker Solar Probe will soon fly closer to the Sun than any spacecraft before it, about 4 million miles from the visible surface. But getting that close to the Sun requires some fancy orbital mechanics. It takes 55 times more energy to go to the Sun than it does to go to Mars. Why is it so hard to get to the Sun? The answer is related to why Earth doesn't just fall straight into the Sun, despite the strong gravitational attraction. Earth, and everything on it, is traveling very fast, about 67,000 miles per hour, in a direction that is basically always sideways relative to the Sun. If you launch a rocket from Earth straight toward the Sun, it won't lose that sideways speed, and so it will miss the Sun. The only way to get the rocket to go right into the Sun is to cancel all that sideways motion. Leave even a little bit, and it will miss the Sun and enter a new orbit. To cancel Earth's motion, you have to launch the spacecraft backward as fast as Earth is hurtling forward. But 67,000 miles an hour is really fast. Spacecraft have to go upward at only 25,000 miles an hour to escape Earth. Getting to Mars only requires a bit more speed, 29,000 miles an hour. New Horizons, which NASA sent rushing out to Pluto, managed 36,000 miles per hour, or a little more than half what it would have to do to hit the Sun instead. Since Parker Solar Probe plans to fly past the Sun, it doesn't need to cancel out all of Earth's sideways speed, but it does need to remove 53,000 miles per hour of it. That's why it's using one of the most powerful rockets available, and additional gravity assists from Venus over a period of several years. In this case, rather than speeding up the spacecraft, as in a typical gravity assist, Venus slows down its sideways motion, so the spacecraft can get close to the Sun. When it finally does make its closest approach to the Sun, Parker Solar Probe will have lost much of its sideways speed, but gained a great deal of overall speed thanks to the Sun's gravity. Parker Solar Probe will hurtle past the Sun at 430,000 miles an hour, the very first human-made object to get that close.
Scientists have now spotted signs of a structured boundary between the Sun and the rest of the solar system. The Sun is not a hard ball in space, nor is it a giant ball of fire. Instead, it's a mass of charged particles and magnetic fields. This material extends outward, flowing beyond the surface of the Sun, creating an atmosphere that spreads throughout our solar system. But the transition is not perfectly seamless. Our star can be characterized into layers. Each region has its own temperature ranges and special properties. We call the Sun's atmosphere the corona, the steady breeze of particles flowing out from the Sun and filling the space between the planets is the solar wind. New research indicates that there is a discernible transition between the corona and the solar wind. This difference is marked by a visible change in the consistency of solar material departing the sun. About 20 million miles out from the sun, the very nature of the solar material changes, and the sun's magnetic field no longer controls its movement. At this point, the flow becomes more turbulent. Like water from a squirt gun, the plasma starts as a stream, but then breaks into drops. The farther out it goes, the weaker the sun's magnetic control of the material, and the less clear its form becomes. To find this transition, scientists took images of the faint solar wind and used an algorithm to dim the competing brightness of background stars and dust. These are the first movies of the solar wind itself in a previously unmapped region, helping us understand what's flowing from the sun through the space around our planet and out to the edges of our solar system. Crucial information as we continue to explore.
The sun's core is the hottest part of the sun, but our star's temperature doesn't behave as you might expect. The core is roughly 27 million degrees Fahrenheit and 10 times more dense than gold. As you move outward, the layers of the sun become cooler and less dense. Something unusual, however, occurs when you reach the outermost layer. While the surface is around 10,000 degrees Fahrenheit, the corona, the sun's outer atmosphere, is several hundred times hotter. That's the opposite of what happens with a fire. When it gets cooler, the farther away you get. Scientists call this the coronal heating problem. It remains one of the greatest unanswered questions in astrophysics. The corona extends for millions of miles and continues outward as the solar wind, which bathes Earth and the entire solar system. This tenuous region consists of superhot elements such as hydrogen, helium, and iron. There are a variety of theories for what mechanisms could be adding that extra heat into the atmosphere. Scientists think it may be the result of the sun's convective motion that acts like boiling water and tangles magnetic fields on the surface. One theory suggests these tangled fields create small waves that push particles and heat from the surface into the atmosphere, like how ocean waves push surface. Another theory suggests small bomb-like explosions from the realignment of the sun's magnetic field create heat. Many scientists think it may be a mix of both. We've studied the corona from Earth and satellites, but to solve our star's biggest mystery, we have to make direct observations from the region itself.
Imagine standing around a roaring campfire, roasting s'mores. You feel the warmth of the flames as the marshmallows crackle. Now, back away. You get cooler, right? That's not how it works on the sun. The visible surface of the sun has a temperature of 10,000 degrees Fahrenheit. Backing away from the inferno should cool things down, but it doesn't. Instead, the sun's upper atmosphere, or corona, sizzles at millions of degrees, a temperature 200 to 500 times higher than that of the roaring furnace below. For more than a half century, astronomers have tried to figure out what causes the corona to be so hot. It's one of the most vexing problems in astrophysics. Solar physicist Bart Pontieu of the Lockheed Martin Solar and Astrophysics Laboratory says, the problem of coronal heating was first discovered in the 1940s. The problem involves a variety of complex physical processes that are difficult to directly measure or capture in theoretical models. On June 27, 2013, with campfires blazing around the USA, NASA launched the Interface Region Imaging Spectrograph, IRIS, a space-based solar observatory designed to get to the bottom of how the solar atmosphere is heated. IRIS studies the transition region between the sun's surface and the corona, explains Pontieu, who is the science lead of the observatory. It can track the temperature and motions of hot gas at unprecedented spatial, temporal, and spectral resolution. Most researchers agree that the corona is probably heated in several different ways. For instance, plasma waves from the sun can rise into the corona and crash, depositing their energy there. At the same time, heat bombs could be going off. These explosions happen when magnetic fields in the corona crisscross and realign, exploding like a miniature solar flare. One of the big questions of coronal heating has been, is the corona heated everywhere at once, Or is heat delivered in discrete, bomb-like events? Dipanshu says, these two possibilities are very different, but the distinction can be difficult to observe. The problem is the corona is a great thermal conductor. If a heat bomb goes off, the resulting heat rapidly spreads out over a large region. Blink, and it looks much the same as uniform heating. Fortunately, Iris never blinks. A recent observation by the observatory's spectrographs has found evidence for these discrete, explosive events. Paola Testa of the Harvard-Smithsonian Center for Astrophysics, lead author of the paper reporting the results, says, because Iris can resolve the transition region 10 times better than previous instruments, we were able to see hot material rushing up and down magnetic fields in the low corona. This is compatible with models from the University of Oslo, in which magnetic reconnection sets off heat bombs in the corona. Testa emphasizes that other heating mechanisms may be at work too. Even so, these new observations could help tease out how much of the heating comes from discrete heating events, helping researchers sort out a decades-old puzzle of great complexity.
What we're looking at right now is imagery from the Solar Dynamics Observatory. All of the dynamics and activity that's going on in the solar corona, the sun's atmosphere, which is what I study. We're watching the sun rotate right now. This is one of the basic features of the sun, and it takes about a month for the sun to rotate fully around and to see the same spot on the sun come back. We're seeing the sun rotate so quickly in this movie because it's time-lapsed. When the sun jumps around, that's actually the Solar Dynamics Observatory moving around and pointing in different directions. Sometimes they have to point away from the sun so that they can calibrate their sensors, the cameras. When we see the frames go dark, that's eclipse season. So that's when the Solar Dynamics Observatory, which is orbiting the Earth, goes behind the Earth, and the Earth is between the Solar Dynamics Observatory and the sun, and so the Earth eclipses the images. These really bright spots, called active regions, have concentrated magnetic field and concentrated heating because of this extra magnetic field and the extra energy due to it. There are more active regions during solar maximum and fewer active regions during solar minimum, and often these active regions can lead to solar eruptions such as solar flares and coronal mass ejections. I study the coronal heating problem. That is, why is the solar corona so much hotter than the solar surface below it? And we know that it has to do with the magnetic field, which is constantly dynamic and evolving and ejecting energy into the solar corona. And you can really get a sense of that when you watch these Solar Dynamic Observatory movies.
Thank you for joining us on this incredible journey to the sun. We hope you enjoyed learning about the sun's corona, the complexities of space travel, and the incredible science that keeps our closest star burning bright. If you love this video, make sure to give it a thumbs up and share it with your friends. Stay tuned for more exciting content from the cosmos, and remember to subscribe to our channel for your regular dose of space exploration. Until next time, keep looking up and wondering about the universe. Stay curious, stay inspired.